Okay, so this is about gating design evaluation. In particular, we will look at how do you verify a given gating design. We will look at the various fillability aspects. For example, we will look at what is the filling time, is there going to be mold erosion, we will track some velocities, and even at the end of this we will look at how do we evaluate gating system, especially in terms of yield. Now, once we design the gating and we already have the design in terms of dimensions and location of the sprue and runners and the gates, the first thing to look at is as the metal flows through the gating channels and comes out into the mold cavity, what is the velocity through the gates. Okay. Now, to do that, we can follow our original equations. We look at the head in the pouring basin. If you are pouring from a ladle and then we have to add the ladle height also, that adds to additional head of metal, and that, let us say, is H pouring plus H basin, and that gives us the total velocity at the bottom of the basin as root over 2g H pour plus H basin. Now, that becomes the velocity at the top of the sprue. Then the sprue bottom velocity is nothing but the total head which is at the bottom of the sprue, which is height of the sprue plus height of the basin plus pouring head. Now, if you are pouring into basin and then there is a dam, what we discussed earlier, and then the metal flows over the dam into the sprue, then you have to worry only about the height difference between the height of metal in the basin and the bottom of the sprue, which means essentially sprue height, we can say that. So, depending on the pouring head, we have to look at the velocity of the metal at the bottom of the sprue. That is your sprue velocity sprue dot 2. Now, once we have the sprue velocity, and we can calculate the gate velocity by using the gating ratio. So, here we see velocity at the gate is equal to the exit velocity at the sprue multiplied by the area of sprue by area of gate, which is the gate, which are gotten from the gating ratio. Now, from the in gate, we also learned how to calculate the impingement velocity or impact velocity of the metal on the mold. We can track the projectile motion of the metal in the mold, and then finally we can find out what is impact velocity and the impact angle. Then we also learned that if the impact velocity is more than the critical velocity, typically 2 meters per second in sand molds, it can create a damage. Next, we look at what is the actual time it takes to fill the mold cavity. Now, how do we do that? Here there are a couple of complications. One is, as the metal is entering the mold cavity and rising in the cavity, once it rises above the gate level, the back pressure of the metal head on above the gates will reduce the total head available for filling. So, the net head is nothing but the original head minus the back pressure head, which is the height of metal rising above the mold cavity, and because of that the velocity keeps on reducing once it rises above the level of the gates. So, that is one complication, is the changing velocity of the metal as it enters the mold cavity. The next complication in most industrial practical castings is that the cross section area is not the same. As the cross section area is changing, if you take a slice of the cross section and let us say finite thickness, the slice volume is no longer same. Different slices have different volumes. So, velocity is changing, which means flow rate is changing, the slice volume is changing. So, the time it takes to fill a given layer in a casting is no longer constant. Now, in a real casting, we have to account for both these changes as we estimate the total filling time. So, we can do that by integrating. What you see is the time actual is nothing but integration over 0 to h, which is the height of the casting, and we have the instantaneous cross section area AI divided by instantaneous velocity considering the head and the area of the gate multiplied by the slice thickness dh. So, if we can run the integration, which can do hand calculation for a simple casting, but for a complicated casting we can use a computer program. We can calculate the actual estimated filling time. Now, if that filling time is very different from the ideal filling time which we started off with, then we need to go back and change your gating design. Essentially, if your estimated filling time from this equation is more than the original ideal filling time, then we need to increase the gating size or reduce the gating size. Reduce the gating size. Not really. Increase the gating size, because increased choke area will let more flow metal in, and then we can reduce the filling time. On the other hand, if our actual filling time is less than the ideal filling time, we need to increase the choke area, and thereby correspondingly also increase the sprue and runner areas. That is how we can control and adjust the the estimated filling time of the mold cavity with the ideal filling time. As you can see, and I was asking you that question earlier, if you have a casting which is bottom heavy versus a casting which is top heavy, okay. Let's take the same casting. Let's take a casting which has more cross section area at the bottom and less cross section area top. And let us assume that the gate is in the middle of the mold. Okay. Now, if the metal fills in, and I have two options now, I can keep the heavy portion in the bottom, or I can turn the casting around and put the heavy portion in the top. Which layout is likely to fill faster? Okay. The one which is bottom heavy will fill faster because initially the metal velocity and the flow rate is high. With the high flow rate, I am filling up a greater volume, and thereby I am going to fill the entire casting faster. If I reverse the casting and keep the heavy portion on the top, by the time the heavy portions or the big cross section areas are filling, the velocity and the head are already reduced, and the filling time becomes much more to fill up that heavy area. So it's always a good idea, if you want to fill fast, keep the heavy portions in the bottom. Okay. Now we have to track one more velocity, which is the vertical velocity of metal in the mold. This velocity is the rise of metal in the mold cavity. Okay. If you assume the original picture of, we said the velocity is reducing as the head is reducing, and assume a constant cross section area of the casting. Let's take for a starting point. The vertical velocity of metal in the mold initially will be constant until the metal reaches the level of the gates. Once the metal crosses the gate area, what happens is now the velocity is coming down, and the vertical rate of rise of metal in the mold cavity is slowly comes down. That is for a constant cross section area, let a rectangular block casting. Now if you take a real life casting like this, let's take, it's not a real life, it's a simplified real life casting, let's say H kind of a shape. If you see the metal stream coming into the mold cavity, first it hits the left side of the H leg, then once it fills up the left leg, it is flowing over the horizontal portion, the middle leg of the H, and then flows on the other side. Now if you track the vertical velocity, initially the vertical up velocity is 0 before the metal stream starts. As the metal stream is still falling into the mold cavity, still there is no vertical velocity. Once the metal starts rising in the mold cavity, you see some number here, let's say it is 0.1 meter per second. Okay. Now as long as the metal is filling up, if you see the fourth and fifth pictures in this slide, the vertical velocity is still constant. And now in the last sixth picture here, you see that the metal is just crossing over the horizontal leg. At that instant of time, okay, if you see the next one, this sudden fall in the vertical velocity. It was earlier 0.1 meter per second, now it's only 0.03 meter per second. Why is it happening? Because the rate of metal coming in is same, but now it has to fill up a larger cross section area in the middle of the casting. As that area is filling up, the vertical rise of metal in the mold cavity is coming down. Okay. Now once and if you see it further coming down from 0.03 to 0.028, because now metal, because of the lower head of the metal, it is also, the velocity itself is reducing. So I have increased cross section area and reduced flow rate, so we see from the bottom two pictures, the vertical velocity is further reducing. Okay. Now if you see in the very last bottom right, this is again an increase in the vertical velocity. Why has that happened? Because now once the middle large area is filled up, the top portion again the cross section area is small. So you have, although the velocity is coming down because of the lower head, now area is suddenly reduced, and because of that we again have you see a last spurt in the vertical velocity. Now why is it important to cover and look at this vertical velocity? Several reasons. One, we have seen earlier that if there is a sudden change in the vertical velocity, initially let's say it comes to a halt and then suddenly starts flowing again, these layer of metals, once it comes to a halt, it can freeze on the layer, and the new layer coming in, there could be a lap. The fusion between these two layers need not be very good. That is your one kind of a defect. The other defect is, if you see the last portion of casting filling up here, the very last portion when there is a sudden increase in vertical velocity, the venting of the air in the cavity which has to escape to prevent the gas entering the mold cavity, there can be problem with that. Okay. There is a sudden vertical spurt in vertical velocity, air may not have enough time to escape, and you might get either a blowhole or a misrun because the last part doesn't fill very fast. Head is low, it's slowing down, and a sudden speed increase with air pocket being formed doesn't allow the metal to actually rise. Okay. So this rise in speed can actually be arrested because of the lack of escape of air from the venting. So venting in these areas actually is very critical. Whenever you have a sudden change in cross section area from large area to small area, and very sudden change of vertical velocity can happen, unless you weld properly, you can end up with a blowhole or a misrun. Now let us look at the filling uniformity. That is the last criterion in good filling. If you remember, we talked about complete filling, then smooth filling and uniform filling. So in uniform filling, if you look at this, the first example here, some kind of a wheel casting. If you put the sprue on one end and the gate at one end, by the time the metal flows around the casting and goes to the other side, the temperature is falling, it's picking up slag and perhaps air also, and you may not get uniform properties in that. A much better solution in this case, if you have enough space in the middle of the casting, is to put the sprue right in the middle and connect the sprue with multiple gates. In fact, you can completely bypass runners here and improve the yield also. Instead of putting a runner outside the casting, you are putting the sprue in the middle, bypassing the runners and directly connecting the gates to the sprue. Much better uniform distribution of metal in the mold cavity, and then you can get much more uniform properties in this casting. In other example here, we see that there are two cavities connected by a sprue and the runners. Now we have put a sprue at one end. As you know, the metal is going to flow to the farthest gate first, and that cavity will fill faster. The second cavity fills little later. If you want little more uniform filling of both cavities, I would rather have the sprue in the middle. Then I get, if they are either equally good or equally bad, but either way I can control the properties much better if they are more uniform. So now let's go back and look at our three criteria once again. So we said complete filling, and essentially what we mean that we don't want any unfilled regions, especially long far regions which are thin and far away from the gates. We want to make sure they are filled properly. And how do we do that? We need to have sufficient temperature, sufficient velocity, and minimum resistance of air and other gases from the mold cavity. One criterion here which we can add here, which is very useful to evaluate the gating systems, is the ratio of filling time and solidification time. It is especially important in thin wall castings. In a heavy casting, it's not very difficult to check, because a heavy casting filling time is a small fraction of the solidification time. It takes seconds to fill, maybe minutes, maybe hours to solidify. That's not a problem. But in a thin wall casting, where because the weight is small and the filling time is low, the solidification time also is very low because of the high heat transfer rates. So ratio of filling to solidification, if it's let's say close to 1 or 2 or even 5, we have a problem, because as it is filling, it is solidifying, and it may solidify completely before it reaches all the ends. So we want a low value of this ratio. Low filling time and long solidification time is good for complete filling. That's the reason in pressure die casting I can have a problem, because their filling time as well as solidification time both are very short, and the ratio could be very high. Now then second criteria which we mentioned was smooth filling, and we said we want smooth filling to prevent erosion, oxidation, air aspiration and things like that, and we said we can do it by minimizing turbulence. How do you minimize turbulence? Minimize velocity and obstructions. Even if you have little high velocities, if the metal is flowing in a straight line or flowing smoothly, there is no problem, but the moment it hits a lot of obstructions like bends or expansions or contraction, we are going to have more turbulence. So what do you do here? The ideal way to check or have smooth flow is to minimize the velocities. In case of ferrous to maximum 1 meter per second, in case of non-ferrous to maximum half meter per second. The third one was uniform filling. We said if it's a one large casting and if it's symmetric casting, try and have multiple entry points. And if it's multiple castings in multiple cavities in the same mold, try and have gates and sprue and runner in a symmetric fashion, so they all start filling at the same time and end filling at the same time. Okay, that is what we mean by uniform filling for one casting or multiple castings in the same mold. Now finally we look at how do we evaluate gating system in terms of yield. Okay, and now we are here looking at the total yield. Earlier we looked at the feeder yield only, but now we look at the gating contribution also to yield. So what is this? Yield is equal to number of castings made in the mold cavity divided by the total metal poured, which is n into volume of casting plus volume of all the feeders plus volume of the entire gating system. Okay. Essentially total part volume divided by total metal poured in the mold cavity. Yield is usually calculated on a per mold basis, as we have seen here. Now how do we maximize yield as far as gating design is concerned? By minimizing the gating weight. But you can't minimize gating weight as it is. We have already looked at how design is to be done very carefully for a given filling time and flow rate and so on. So we cannot just like that reduce the cross section area. The smartest decision you can look at is to look at the sprue location carefully. You know that gate locations are more or less frozen. You know how many gates to put and where you want to put that. You can't really have too much compromise on that. What you can really play with is where do you put the sprue, because sprue has to be connected to the gates to runners, and runners contribute significant amount to the weight of the gating system. So you put the sprue in such a way the total runner length is minimized, you can maximize the gating yield considerably. To summarize, we looked at how do we evaluate a gating system. We looked at velocities, especially impact of metal on the mold cavity. We looked at how do we estimate the total filling time of a mold cavity. We also looked at the vertical velocity of the metal in the mold cavity, and that should be uniform, otherwise you can have lap or misrun or a blowhole. And then the filling sequence in a complicated casting could be controlled. Especially we said it should be as uniform as possible by putting multiple gates and more symmetric gating systems. And finally we looked at the gating contribution to yield and how we can try to maximize that by strategically locating the sprue to minimize the runner length. So this lesson is about how do you know the gating system is rightly designed. Okay. And we just talk about the fillability criteria once again and see which ones we are really satisfied or not. And we talk about gating optimization and gating yield. Now in this what you see is the first point you have to worry about the metal coming out from the gate and hitting the mold cavity. Okay. And it's possible to calculate the impact velocity and the impact momentum, which you have seen from the science part of it already. The part we have to worry about more is what is the actual filling time of the mold cavity. Because you have designed the mold cavity, let us say for 8 seconds ideal filling time. How do you know it's actually going to fill in 8 seconds time before you go to shop floor? Can you do a calculation of filling time? It's possible. The only two parameters you have to worry about is, one is as the metal is filling in the mold cavity and the cross section areas are changing. If a rectangular block is very easy calculation, a real casting cross section areas are changing. And number two, you have the metal as it comes into the mold cavity and metal rises above the gate location, there is a backward pressure from the metal to reverse pressure from the metal onto the head. Head reduces, so velocity reduces. So as the metal rises above the gates, my head is continuously reducing, velocity is continuously reducing, cross section areas are changing, but all this can be possible to be estimated by putting up an integration. With simple casting you can do hand calculation, otherwise you can write a simple program to calculate the filling time of mold cavity. Obviously castings which are like this and castings which are like this, assuming gate is in the same location, they will fill differently, although volume is same. If the casting bottom is more area than top area, it will fill fast, because initially metal flow rate is high and filling up more volume with the initial high flow rate. Okay. Later on flow rate becomes less. So castings which have heavy bottoms fill faster than castings with heavy top, if the gate is in the middle of the mold. So we can estimate the filling time. We can also track the vertical velocity of metal rise in the mold, because we talked about lap formation and few other problems. Okay, even blowholes depend on how fast the metal is rising in the mold. So some other problems can be caught if we can track the vertical rise of metal in the mold. Wherever you have sudden big horizontal area, you can have a problem of metal slowing down vertical velocity. If it slows down, venting is good, but then lap formation and blowholes can form. So here is an example of how the vertical velocity is changing slowly and it slows down. At the end of the casting, if you see, bottom row if you see, initially it was 0.1 meter per second, then it slows down. As the horizontal portion is filling up, vertical velocity is slowing down dramatically, almost zero. Then once the horizontal portion is filled up, again it goes back to a little higher up. So that can be tracked by simulation now. These are all results from simulation software. Okay, and filling sequence itself, last one of the things we mentioned is if we can make it more uniform. Your wheel casting, instead of putting the sprue outside, if the wheel is big enough, if you can put the sprue in the middle and then put 4 gates directly, no runner required. Much more uniform filling of the cavity and much better yield also, because you're not wasting the runner volume here. Okay. So 3 last final rules of gating design. For complete filling, we have to ensure that the filling time is much smaller compared to solidification time, right? And especially important in thin wall castings, where solidification time can be also very short. So thin wall castings, you have to really fill fast so that your filling time is lower than your solidification time, otherwise you have unfilling problems. What about second one? Smooth filling. Whatever tricks we talked about so far, head, your gating ratio, and finally if everything else fails, filters. Using that, you can slow down the velocity to under 1 meter per second for ferrous castings. And finally, uniform filling by making sure you have more gates, more symmetrical gates, sprue in the middle if possible, and filling is more uniform. And so you have uniform properties of the part here. And now you have the final yield calculation equation, where you say yield is equal to number of castings in the mold cavity, assuming there are common gating and common feeders, divided by the total poured weight in a mold. This is the yield per mold. So the casting or part weight divided by the total poured weight gives you the yield per mold cavity. Okay. And how do you improve the gating contribution to yield? You try to make smaller gates. Okay. Try to, most strategic decision here is where do you put the sprue so you minimize your runner length. That contributes to gate much more than anything else. Everything else will affect the quality also, so you don't want to meddle with that. The sprue location to minimize runner length is the best thing that you can do to minimize the gating contribution to yield or improve. Okay, so we looked at in this lesson quickly how do you evaluate gating system by looking at velocities, the distribution and total filling time of the metal. Okay, and how do you maximize the yield by minimizing the runner length, essentially by placing the sprue in a strategic position. Okay.